So I want to start this new video just summarizing the main concept of the previous lessons regarding the Helmholtz model, in which the total compensation is achieved in a well-precise zone with a single layer of binded cations, ensuring an electric field completely localized and so potentials profiled that decrease in a well-precise region and then is still maintained constant. Whereas in the Grahame-Chapman model, we know that due to the lack of this assumption, we are able to appreciate the presence of a diffuse layer. What assumption? So basically, the Helmholtz model is based on three important assumptions. The lack of molecular nature concerning ions, the lack of molecular nature concerning the medium, for instance, water, with a certain permittivity, and even the lack of thermal motion. Whereas in the case of Grahame-Chapman, we are considering the thermal motion, and in this case we have something that tries to push apart cations from the surface with an energy that is quite close to the absorption energy, and so we have just a statistical distributions of cations always equal in each single infinitesimal layer if we are in equilibrium due to the compensation between migrations and diffusion as described in the previous lessons. And so we have an exponential profile described from the Debayuka approximation, the Debayuka equation. Now I want to start speaking about another more precise model, that is the Stern model. So basically, passing from the Helmholtz one to the Grahame-Chapman, we have eliminated this assumption. And now, passing from the Grahame-Chapman to the Stern model, we are even eliminating this assumption. So we are considering the same of a Grahame-Chapman model, but with more attention on the molecular nature of the ions, since until now these ions were treated only as a single point charge. So I can start cancelling this and this one. The Stern model. So the Stern model is a quite smart model that, for a certain point of view, collects a result from the Helmholtz model together with a result in the Grahame-Chapman model. So basically, what the Stern model tells us is that we need to consider the molecular nature of our ions, for instance, our cations. And since we are able to collect physically ions with a specific volume, with a specific size on the surface of an electrode due to a compensation mechanism, basically we can say that we have a plane of maximum approach. What does it mean? So we have again our electrode, we have the negative polarization, the classic examples we have done, and we know that there are some positive charge distributed in the Grahame-Chapman and diffuse layer. But in this case, since we are looking also at the molecular nature of these cations, we can say that exists a minimum distance that is always present. So we have always a distance that is present due to the approaching of these real ions, not only single point charge on the surface of the electrode. And so what does it mean? That we have a first layer in which we have a plane, that this one, the plane of maximum approach, and only later we only further we have again a diffuse layer. So basically, from a functional point of view, as always our final aim is to describe this, we can say that, hoping that this time could be visible, if this is the surface potential, we have a plane of maximum approach, that is this one, maybe. And so we have that also in this case exists a localized electric field due to the absorption and the formations of this single layer, and so we have a decrease in the potential having the same profile of an Helmholtz layer, and only later we have the diffuse layer. So a component that is quite close to the Helmholtz model, and a component that is described with the Bell-Euclid's function, so the diffuse layer typical of a Gowee-Chapman. The Stern model is a quite smart solution that collects some result from the Helmholtz plane and the Gowee-Chapman. So we have a real single layer of binded cations concerning a minimal distance, since we have actually a real physical dimensions of cations, and only later we have a diffuse layer. And so the profile is this one, and then an exponential profile again, as in Gowee-Chapman. Now we can pass from the Stern model to probably what is nowadays one of the most interesting and precise, that is the Grahame model. So in the Helmholtz model we have solved the function potential versus distance, taking consider of the lack of molecular nature of solvent, the lack of molecular nature of charge, and the lack of thermal motion. So three assumptions. In the Gowee-Chapman we eliminated one assumption, so we are considering actually in the Gowee-Chapman the presence of thermal motion. In the Stern one is even more precise, because we are considering the molecular nature of the molecules, the ions, and so the last type of model is the Grahame one, in which we are eliminating even the last assumptions, and we are considering now even the molecular nature of the solvent, the medium in which cations are dissolved. So we have the Grahame model. So the Grahame model is similar to the Stern one, but in this case we are taking consider about the molecular nature of the solvent, for instance water. So let's imagine to consider an electrode negatively charged, and in the presence obviously of cations, but in this case the cations are surrounded due to a solvitation process due to the presence of water molecules. So we have solvitation water molecules. The green one. So we have that the green is a water molecule. What actually the Grahame model tells us is that we can have different steps of potentials profile, also taking consider about in which way the water molecules are oriented also toward the electric field. What does it mean? That the Grahame model described at the very beginning, we do not have positive cations, but we have a layer that is composed of, if we want to write, to design this better, is made of oriented water molecules directly absorb on the surface of this electrode. We have some cations, some anions maybe, or general ions, and again. This is take the names of inner Helmholtz plane. Inner Helmholtz plane, high HP. But there is a smart things that should be focused here. We have a negative charge. But how it's possible? We have a negative surface and the absorptions of a negative charge. What does it mean? Well, this is just a chemisorption. And so the Grahame model taking even in consider about possible chemisorptions, and so an absorption that is present regardless the nature of the charge. And so what does it mean is that if we are describing our potentials profile versus the distance, we can even have an increase in the starting potential passing from the surface to the inner Helmholtz plane. Why? Because we are increasing maybe the number of negative charge. There is one negative charge more here, and so the potentials can even increase due to a chemisorption. And only later we have the classical Stern model. So we have the presence of physisorbed cations in a layer that in this case is not anymore known as plane of maximum approach, but is basically take the names of outer Helmholtz plane. Outer Helmholtz plane. And also in this case, basically we are acting as a sort of Stern layer, and a localizing electric field leads to a drop of the potential in this way. Exactly in the first part of the Stern model, known for which this section between the inner Helmholtz plane and the outer Helmholtz plane is known as Stern layer. Obviously, it's important to say that since we are considering even the molecular nature of this solvent, we have solvatation molecules. Here, 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 and so on. Also for this one, for this one, for this one, and so on. But what is interesting here is that we have obviously an outer Helmholtz plane that is not anymore the plane of maximum approach, even if we have some interesting similarities with the Stern layer. Because in this case we are even considering the molecular nature, and so the output Helmholtz plane, it will be more distance with respect to an hypothetical plane of maximum approach in the Stern layer. And what is interesting is that on the inner Helmholtz plane we have the presence of oriented water molecules that are not involved in a solvatation process. And for the reason, since we have a huge orientations under an electric field, the permittivity here is low. But in this case, since we have a different orientations fighting the electric field, because water molecules are involved in a solvatation process, we have a zone having a higher permittivity. And so we are even taking consider about the different permittivity value in different zone of the medium with respect to different distance from the electrode surface. And later, what is still remain is the last zone in which we have our well-known diffuse layer as in the Grahame-Chapman. And so, the final exponential profile, this function, is following in the very precise Grahame model these particular types of trend.